Welcome to this lecture series in real analysis. We are starting a new module which will be about continuity, and this will be a central notion for all of analysis, but particularly this lecture series. And all we need to know fundamentally is the language of sets and functions and what is meant by open sets. So let me not get into the details of these definitions. We have used these notions infinitely many times by now. Okay. Here are some problems for practice. And now let us get started. So first, let us discuss why or what is the idea behind continuity. So given a function, let's say from all the reals to reals, we say it is continuous if sufficiently nearby points in the domain go to nearby points. This may not be clear as of now, but that is the philosophy. Ultimately, we will justify this, or we want to justify that, this is a meaningful definition, and whatever is the formal definition must be a manifestation of it, a precisation of it. Okay, before we give a formal definition, at the very least, we should have some guiding examples in mind as to what we are trying to capture. So we have drawn a graph of a function. Let's say this is the graph of x square, x going to x square, that function. So I'm assuming you're familiar with the notion of graphs as discussed in high school. We just draw something in the plane, and I'm sure you know what that means. So such a function sounds like a continuous function, right? So the more informal idea behind continuity is that if you can draw the graph of the function without lifting your pen, that's even more informal than that. But that is certainly what is motivating this and what is going to ultimately give us the formal definition. So clearly here you can draw this without lifting your pen. So we would like to call this a continuous function. Whatever is going to be the formal definition of a continuous function should allow this function to pass as one. Similarly, this one should also be a continuous function, as we can draw the graph of it without lifting a pen. But this shouldn't pass as a continuous function. Here, when we go from here to here, suddenly we are jumping and we have to lift our pen. Okay? So whatever is the definition of continuity, it should respect these two and disrespect this one. Okay. So first we will nail down or put down some preliminary definition based on which we will give our formal definition of a continuous function. Okay, so first we will define what is called, or what I am calling, the epsilon band. This is not a standard terminology. So first of all, we write this notation R2. This is the Cartesian product of R with R. So this is of course equal to this set. And we imagine it as our plane, and this is called the x-axis, which is all the points where y is 0. This is called the y-axis, which is all the points where x is 0. Surely you're familiar with these notions from high school coordinate geometry. Okay, now let a comma b be a point in R2. So we have chosen an arbitrary point in R2, and here is your figure. Ignore these horizontal lines for the moment, and let epsilon be greater than 0. Okay, then we define the epsilon band about the point a comma b as something. We will write it down, but what is the idea? We have this point a comma b. You draw a horizontal line epsilon distance above. So you go epsilon distance vertically above and draw this horizontal line. Go epsilon distance vertically below and draw this horizontal line. So this line is nothing but y equals b plus epsilon in our coordinate geometry language. And this line is y equals b minus epsilon. And everything strictly between these two lines is the epsilon band about the point a comma b. It looks like a band, and epsilon band because we are taking the thickness or the semi-thickness as epsilon. Okay, so formally, how do we write it down? It is nothing but this set. All the points x comma y in the plane such that the distance of y from B is strictly less than epsilon. So that's precisely what we just said in words. Okay. That's the epsilon band about a comma b, and note that this is not sensitive to the x coordinate. So if you take two different points, a comma b and a prime comma b, so that the y coordinate is the same, the epsilon band around this will be same as the epsilon band around that. Okay, so very simple definition, and let's move on. Let us also recall what is meant by the graph of a function, and we will give a more formal definition to it. Fix any subset A of R. Well, and if it is just some arbitrary subset, we may not be able to draw it very well. If it is a very really messed up subset, like let's say the set of rational numbers, it is very hard to draw it. But it doesn't matter. We can still define what is meant by the graph of this function. So how do we define it? The graph of f is defined as this particular subset. The notation is this, and it is all these points in R2 where x varies in the domain of the function. Okay? So the graph is a subset of R2. We draw it as a subset of R2, but we should formally know that it is actually, by definition, a subset of R2. And above every point of A, you go fx distance above and mark this point, and that will constitute the graph of f. As an example, if you take this function, which takes x to x square, then this white thing is the graph of f. So that's a very simple example. Okay. So let's move on. Now we will talk about restriction of a function. This I am also sure you already know. So fix a function. This is nothing to do with any real numbers or anything. This is a very, very general concept, purely set theoretic concept. So fix a function f from a set x to a set y, and let a be a subset of x. So the restriction of f to a is defined as the map or the function. By notation, it is, we may write this, or we may also write, okay, I will discuss the other notation. But what is the definition? The definition is underwhelmingly little a going to f of a. So all we are saying is a is a subset of x, so every point of a is a point of x. So it is legitimate to ask for this thing, and that's it. You kind of forget what is outside of a and obtain a function. This may sound like a very vacuous or very useless thing, and in some sense it is, but no, it helps us talk about things efficiently. All right, so the other notation for the same thing is, instead of writing that, we may write f and then a bigger, sorry, not a bigger, but you may write a in front of this bar rather than below it. And I might use both of them in the same slide also. Okay, so that's that. And in terms of diagrams, which is a very useful way of recording mathematical information. So this is a function that is given to us. This is the inclusion map. So what is this map? This map is again a very underwhelming map which takes little a to a. Capital A is a subset of capital X. So every element of A is an element of X, and hence this is a legitimate map. Okay, and now you take the composite. So this composite is nothing but the restriction. You may write it that way or you may write it this way. Okay. Fine. So much for these preliminaries. Maybe there is more. Yeah, there is a little bit more. This is a kind of a new definition, I think. I don't think I have defined the notion of a neighborhood before. So fix a point X in R. A neighborhood of X is an open set containing X. Very simple definition. I don't think I even need to give any examples for this. Okay. And let us also record this definition. This is the definition of this is the delta neighborhood. So fix some real number and a positive delta. The delta neighborhood of X is this open interval. The points which are at a distance at most, or rather strictly less than delta from X. That's the delta neighborhood. Delta neighborhood is in particular a neighborhood because it is an open set containing X. So that's that. And now I think we can get started with the main thing. Yeah. So what is the definition of continuity? Oh, this will be hard to explain very well, but I have to try. So fix a subset S of R, and of course we are assuming this is a non-empty set. And for the sake of understanding, you should take S as all real numbers or an open set or something. But the definition will be very general, and it is important that the definition be very general. When we go to general topology in some other lecture series, this generality will actually be very, very useful. So let's not restrict ourselves to just nice sets here. Okay, so we are given some function. And we have been given some point in S. We want to define the notion of continuity of the function f at the point x0. Okay? So we say that f is continuous at x0 if, well, recall the motivational slide where we said points sufficiently nearby to x0 should map to points nearby fx0. That's the motivational thing. So let me verbalize that motivation. So choose a notion of nearness to fx0. Basically choose an epsilon band around this point. So any point in this vertical line can be thought of as a point which is near fx0. In fact, any point in this band, in this entire band, should be thought of as something that is epsilon near fx0. It is in the epsilon neighborhood of fx0. Okay. And to say that points sufficiently nearby x0 map to points nearby fx0 is just saying that there is a small enough delta neighborhood, or is a small enough neighborhood of x0 such that all the points in this neighborhood map within this epsilon band. So whenever you choose an epsilon band around this or about this point, there is a small enough delta such that the delta neighborhood around x0 has the property that every point in it maps inside this epsilon band. This is 99% a precise definition. The only thing non-precise about it is that we haven't written it. And here is the geometric way of writing it. So the geometric way of writing the same thing is the following. If for all epsilon greater than 0, and I have marked these here, I will correlate this with that very soon. For all epsilon greater than 0, there is a delta greater than 0 such that the graph of the restriction of f to this thing, you take the delta neighborhood of x0 and intersect with the domain of S. This should be contained in the epsilon band about this point. Right? So what's going on? Some adversary has chosen an epsilon. This is the notion of nearness that has been chosen by the adversary. And you draw this epsilon band. And what we are saying is that there should exist a delta. For f to be continuous at x0, no matter what is this epsilon, there should be a delta small enough such that the graph of the function above this region, so S was maybe could possibly be some horrible thing, but for the sake of understanding, think of S as the entire set of real numbers. So the graph of f above this region, meaning in the delta neighborhood of x0, is trapped within this epsilon band. So this is kind of saying that if you try to draw the graph of the function near the point x0, you will have to be confined in this epsilon band, and the more stringent the epsilon, meaning the smaller the epsilon, perhaps the delta that you will produce will be even smaller. But this is telling you that you will not need to lift your pen, or this is capturing the idea that you will not need to lift your pen to draw the graph of the function, because the function is not allowed to suddenly fly off. It has to respect this epsilon band in a small enough neighborhood, or the small enough delta neighborhood around the point x0. Okay, so that's very important. So that's the definition, and it may not be completely clear as to how this is capturing the intuition that we mentioned at this point, but it will be clear in due time, and you should mull over it, discuss with friends, etc. But as we go along, we will be able to understand things better and better. Okay, so before we proceed, let me make one more definition. So we say that f is continuous. F is continuous if f is continuous at each point of the domain. Okay? Continuous at all points in the domain. So first we defined continuity at a point. You choose a point in the domain, and then we defined what is meant by continuity at that point. But here when we say f is continuous, we are kind of defining the global continuity of f. So we say f is continuous if it is continuous everywhere in the domain. Okay. So let's move on. So we look at some examples to foster our understanding. The first thing is the constant function, and we want to see that this is actually a continuous function. So fix some function f from a subset S to R, and let's say f of x is, for concreteness, 7 for all values in the domain. So 7 is some arbitrary number I just chose. Okay. So let's see why this is a continuous function. So x0 is some point in S, and here we will mark out this point which is in the graph of f. Okay, so the value above x0 is 7, so we have marked that point out, and draw some epsilon band. Choose some epsilon greater than 0 and draw the corresponding epsilon band. Now what do we want to do? We want to say that f is continuous at x0, meaning we should be able to produce a delta greater than 0, such that if we draw the graph of f restricted to the delta neighborhood of x0 intersected with the domain of f, then that graph should lie in this epsilon band. So can we produce such a positive delta? Of course we can. Just take any positive delta. So take any positive delta you like. Then what is the graph of f restricted to this delta neighborhood intersection S? This intersection S is coming only because the domain of the function is S. If it were all real numbers, we wouldn't need to write it. And for the sake of understanding, it is better to take S as all real numbers. Okay, so what is the graph of the function restricted to this? It is just the constant, just this Above every point here, you just mark out the value 7. So it is of course going to be contained in this epsilon band, right? So that's that. I mean, it's very, very simple. So constant functions are continuous at all points in the domain, so they are continuous functions. Okay, and here is another one, the identity function. So define this as fx equals x for all x. We claim that this is also a continuous function. So let's see why. So let's draw the graph. It helps to draw the graph first in this case. So this is roughly what the graph is going to look like. And let us try to see why this is continuous at, let's say, this point. Okay, maybe I'll move it a little bit. All right, so the corresponding point in the graph is this guy, x0, x0. And let us make an epsilon band around it. Very bad. Okay, we've made some epsilon band around it. All right. Now, what do we need to do to prove that the function is continuous at x0? We need to produce a delta such that the graph of the function restricted to this delta neighborhood is contained in this epsilon band. And can we produce such a delta? Well, such a delta, you can take delta to be epsilon. That works. So why does that work? Since this is a 45-degree line and this is epsilon, this is also epsilon. Okay? So similarly, since this is epsilon, this is also epsilon. So everything, if you just make this kind of square, the graph above this interval, which is nothing but the delta neighborhood around the point x0, the graph of the function is contained in the epsilon band. Of course, you could choose a smaller delta. You could choose delta as epsilon by 2. So in that case, you will be getting this kind of thing. Anyway, so I hope you can see that this function is continuous. Okay, and here I will leave as an exercise. So suppose we have a function from x to r and a be a subset of x. Everything is non-empty. Let a be a point in the set A. Now, if the function f is continuous at A, then the restriction is also continuous at A. This is a very simple fact, easy to prove, but you should prove it formally. This will help you digest the definition of a continuous function better. Okay, so when we say f is continuous, here we are talking about this as the domain. But when we say this is continuous, we are talking about this as the domain. Okay, lastly, let's talk about the square function, the function that we saw earlier. Right? So why is this a continuous function? We will not give a formal proof. The formal proof will come in subsequent lectures. But here, let's just try to see it visually. Choose a point x0 and take the corresponding point in the graph. The color is somewhat horrible. That's the corresponding point in the graph. Make an epsilon band. Okay, and now to prove continuity of the function f at the point x0, we should be able to produce a delta neighborhood of x0 such that the graph of the function is trapped in this epsilon band when we restrict it to this delta neighborhood. And is it? So it should be clear visually. If you take delta as small enough, then indeed the corresponding graph will be within this epsilon band. And this will stay true no matter how small you choose epsilon. The smaller you choose epsilon, the smaller the delta you will need to respond with. Okay, so I hope I have put the point across. All right, so let's see some non-examples. So step function. Let's not try to prove this formally either. Let's just see it. So let's try to say why the function is not continuous at this point. This point is also in the domain of the function because the domain of the function is the entire set of real numbers. Why is it not continuous at this point? The value at this point is this, meaning this number, which is 1. And the point in the domain is also 1. So let's make an epsilon band around, so before we go there, this is our x0. x0 is equal to 1. And let's make an epsilon band around the point x0, 1. So we have chosen some positive epsilon and made the epsilon band. And now, no matter what delta you choose, if you take the delta neighborhood, and let's say epsilon is less than half. So the epsilon we chose, let's say, is equal to half. Our epsilon is equal to half. Now, no matter what delta you choose, some points in the graph of the function, when you restrict the function to this delta neighborhood, are outside this epsilon band. Which points? These points. The point on the left side of x0, they do not map under the graph of the function, they do not lie inside here. You draw the graph of the function restricted to this delta neighborhood. Some points of the graph are outside this epsilon band, and therefore the function cannot be continuous at x0 because no matter what delta you choose, you always fail. So this function is not continuous. You can write down a formal proof almost. From what has been said, you can write down a completely formal proof of it. Okay. This example is a very standard and famous one. So f is a function from reals to reals, and it is defined this way. So what does this mean? This means that it takes the value 1 if x is in... Okay, So what this means is that fx equals 1 if x is a rational and 0 otherwise. So when we write that, this is what we mean. Okay, so this is our function, and we want to see that this is not continuous. In fact, this will be not continuous anywhere. Why is it not continuous anywhere? So, there's no way I can draw the graph of this function, but hopefully I will be able to explain why this is not continuous. So let's talk about the origin. Let's try to see why is it not continuous at the origin. So x0 is equal to 0. And the value at x0 is 1. So this is our corresponding point in the graph of f. And we make an epsilon band where epsilon is small. Let's say epsilon is half. So this is our epsilon band. Okay. And again, no matter what positive delta you choose, some points in the graph of f restricted to this delta neighborhood stay outside of this epsilon band. Because in every delta neighborhood, there will be some irrational number sitting inside. And on irrational numbers, the function takes the value 0. And hence, the corresponding point in the graph cannot be inside this epsilon band. This is a highly discontinuous function in the sense that it is discontinuous everywhere. That was not true for the step function. We showed that the step function is discontinuous at this point, but if you just think about this point, the step function will be continuous here. So it is not discontinuous everywhere, but this is. However, I want to make very clear one point, that if we take this map has the rationals as its domain. This had the reals as its domain. And what is this map? This map is just the same. It takes the value 1 everywhere. Okay, that's this map. So superficially, it may look like this map and that map are the same map, but they are not. This is not even allowed to talk about irrational numbers, while this map has the capability of eating irrational numbers and outputting a real number, even though the behavior of the two functions on rationals is exactly the same. This was discontinuous everywhere, but this is continuous everywhere. Okay, this is a constant function. We talked about constant functions, that constant functions are continuous everywhere. This is far from a constant function. So the point I'm trying to make is that the domain matters. If you change the domain of a function, the continuity may get disturbed. So even though restrictions of continuous functions are always continuous, the restrictions of discontinuous functions could be continuous, could be discontinuous. So the implication doesn't go this way. Okay, so let's be very clear about this thing. And if this is confusing, that should be a cue for you to stay on these things and clarify them. Clarify them for yourself by thinking about them. Okay? So yeah, so that's the end of it. As usual, like, comment, share, subscribe, and I will see you next time.